section 3.2, domain and range. When considering a function, the two things we want to consider are the function's domain and the function's range. The domain of a relation is a set of permissible values for the input variable. The range represents the set of the output variables that correspond to the domain. Now, one thing to note, the relation does not have to be a function in order to have a domain and a range. But since our main focus is going to be on functions, we are going to look at how to determine the domain and range of a function. Now we're going to determine the domain and range of each relation defined by a set of discrete order pairs. First, we're going to find the domain. Now, the domain is the set of all the values we can input into our relation. Here, our first components, what we're plugging into our relation, are 5, 3, 10, and 6. So we're going to put those numbers in our domain. Now, in the set, the order doesn't actually matter, but just for aesthetics, it does help to put the numbers in numerical order. The range would be the set of all the output values. Here we'll see the output values are -20, -12, -40, and -24. And again, we'll list them in numerical order, even though the order does not matter. So our domain is the set containing 3, 5, 6, and 10, while our range is the set containing -40, -24, -20, and -12. Next, we'll find the domain of range of our second set of order pairs. Our domain, remember, is the set of all our input values, which here are 3, -1, 3, and -3. So putting them in numerical order, you have -3, -1. Well, notice with the 3, they do appear twice in our order pairs. However, whenever we're listing them out for whether it's the range or domain, we don't want to include duplicates. So even if a number appears 2, 3 times as a possible input or output variable, we only want to list it once in its domain or range. So our domain is the set containing -3, -1, and 3. Next, we'll find the range. Well, all of our second components, our output values are 11, 22, 2, and 3. There are no duplicates, so our range is 2, 3, 11, and 22. Now we're going to find the domain and range of each of the following functions that are defined by graphs. When finding the domain, visualize how we could compress our graph onto the x-axis, almost as if we decided to take the graph from top to bottom and smash it so that way it is lying flat on the x-axis. Well, the first point the graph would touch would be here at -2. And if I compress this point here, it would compress here at x equals 1. Now, the rest of the line would compress everywhere in between -2 and +1. Now, remember, the domain is all the possible values we can input into our function, which would be represented by our x values. So we can see our domain would be all the values from -2 to 1, which we can write in interval notation. Since -2 is in our domain, as indicated by the solid dot, we will put a bracket. Since 1 is also part of our domain, indicated by the solid dot, we would also put a bracket. Next, for the range, we're going to think about how the graph would compress onto the y-axis. If I start from the left and right and squish the graph onto the y-axis. Here at the point -2, 0, I can compress it onto the y-axis there. Same thing at the 1, 3, I would compress it there. Every other part of our graph would compress in between y equals 0 and y equals 3. Our range would be the interval from 0 to 3. We would put a closed bracket around 0 because of the closed dot, and a closed bracket around 3, also because of the closed dot. So the domain of our function is -2 to 1, including -2 and 1, and our range is 0 to 3, including 0 to 3. Next, we're going to find the domain and range of our second graph. Starting off with the domain, notice how we have this open dot here at -3, where if we compress down to the x-axis, we put an open dot there at x equals -3, and we have this closed dot ending our graph on the far right, which if we drop it down, would go to 2 on the x-axis. And every other part of our line, if we were to compress it down to the x-axis, we see would shade everything between -3 and +2. So our domain would be the interval -3 to 2. Now, because -3 has an open dot above it, we'll put a parenthesis, and because 2 has a closed dot, we'll put a square brace. Now, as for the range, if we compress the open dot onto the y-axis, we would put an open dot because it's not part of the graph, but it's pretty close to it. And the closed dot on the right, when we compress it to the y-axis, you'd wind up at 2. And our graph does shade everywhere else in between. So our range is the interval 1 to 2. 1 is not a y value for any point in the graph because the only point that has a y value of 1 is an open circle. So we're going to put a parenthesis around 1. 2, we're going to put a square brace because we do have that closed dot that has a y value of 2. So our domain is the interval -3 to 2, including 2, excluding -3. Our range is 1 to 2, excluding 1, including 2. Now to find the domain of our next graph, at the far left, we have this closed dot, where if we compress, you'd have a closed dot here at -2. At the far right, we have an open dot, which when we compress down to the x-axis would be an open dot. And if we drop every point in between on the graph down to the x-axis, you see it would shade everywhere between -2 and +1. So our domain would be the interval -2 to 1, square brace around -2 due to the closed dot, parenthesis around 1 due to the open dot. Now we do have to be very careful when we find the range. If I start at the top left of the graph, I do compress it to a closed dot on the y-axis, and same thing with the open circle. I can bring that over to the y-axis as a 2, and we can tell that everything in between is shaded by the left branch. But we do have to be careful. There is this point here that does also have a y value of 2 on the left-hand side of this graph. Well, if I compress that over to the y-axis, that's going to fill that open circle. And I still have everything else in between all the way down to where y equals 1. So despite the open dot, there is a point on the graph on the opposite side of it that does have a y value of 2. So our range, we can see after we compress the graph onto the y-axis, the smallest possible y value my function can be is 1, and we're going to close it because we do have the point at the very bottom with a y value of 1, and our highest y value is 5 due to the top left endpoint. Despite the closed dot on the point 1, 2, we do include 2 in our range because we also have the point -1, 2, which is part of the graph. So 2 is part of the range. So our domain is -2 to 1, including -2, excluding 1. Our range is 1 to 5, including 1 and 5. Now we're going to find the domain of our next graph. Well, the right endpoint is already on our x-axis, but notice here we have the arrow pointing to the left. That means our graph is going to continue going leftwards forever. When I bring points down to the x-axis, everything to the left of +4 is going to be shaded by some sort of point when I drop it down to the x-axis. As for my domain, everything in the far left is in my domain, so I'll put a -infinity. Remember, -infinity always gets parentheses, and my highest x value is 4. Since I do have the closed endpoint at 4, 0, I will include 4 in my domain. Next, for the range, if I take my point 4, 0, bring it to the y-axis, I can see my lowest point is 0. But again, going to my arrow, it is pointing slightly upward. So even though it's going to be a slope road, it is going to rise the farther left I go. So my range is going to be from 0, close bracket around the 0 because of the point 4, 0, to infinity because the graph is rising forever. The last graph we're going to look at is a little bit more interesting than the others because you can see it's broken up into segments, specifically 3 segments here. To find the domain, we'll focus one segment at a time. If we take a look at our first segment, projecting it down to the x-axis, we would have a closed dot at 1, open dot at 2, and everything else in the middle would be overlapped by some point on that segment. Now we can move on to the second segment, and similar to the last segment, we have a closed dot on the left, open dot on the right. Well, if we bring the closed dot down, it's going to overlap with the open dot, so we're going to fill it in. As for the point 3, 2, we'll bring it down to an open dot on the x-axis and shade everything in the middle. And then in the last segment, similar to the other two, we have a closed dot on the left, open dot on the right. If we project the closed dot down, it does overlap with the open dot from the previous segment, so we'll fill in the open dot, bring down the 0.43 onto the x-axis as an open circle, and everything else in the middle will be filled in. So from what we see, everything between 1 and 4 is shaded, but 1 itself is part of the domain because we do have the solid point 1, 1. However, the point 43 is not part of the graph, nor are there any points on the graph with an x component of 4, so 4 gets a parenthesis. Now, the range of this graph is very interesting. If I take any point on the first segment here, they all have a y component of 1. So that entire segment is going to compress onto 1 on the y-axis. Similar to the first segment, the second segment has a y value of 2 for all of its points. So if I compress the second segment onto the y-axis, I would just have all those points there at y equals 2. And the same thing goes for the third segment. All the y values are 3. So when I compress the line segment onto y equals 3, they would all compress to that 1 point. So all my possible y values for this graph are 1, 2, and 3. Instead of using interval notation, we're going to list it out as a set using the curly braces. And my range is the set containing 1, 2, and 3. I cannot put the interval 1 to 3 here, even though, yes, 2 is in between 1 and 3. But consider a number like 1.1. 1.1 is in the interval 1 to 3. However, 1.1 is not a y value that we can obtain from any point on the graph. So saying that the range is the interval 1, 3 would be incorrect. We're going to find the domain of the following functions defined by equations. The reason why we're focusing on the domain is the range is a little bit harder to find unless you know specific properties relating to the operations or the functions themselves. So right now, we're just going to focus on the domain. When we try to find the domain of a function defined by an equation, we want to think about what operations are being used in the function and which operations have restrictions. The two operations that we know right now have restrictions is division, because we can't divide by 0, and even roots, because the even root of a negative number is not real. And here we're only concerned with real values, and here all of our functions are defined to only be real values. So whatever I plug in has to yield a real number. Well, if I take a look at my function f of x equals 4x plus 3, there is no division, and there are no even roots. So I can take any real number, multiply it by 4, and add that product by 3. There's no way for this function to be undefined, meaning whatever I plug in, I'm going to get an answer out. So my domain is going to be all real numbers, -infinity to infinity. Now we're going to find the domain of g of x, which equals 1 over x squared minus 7x plus 12. In this function, I don't see any even roots, but I do see division. And the one number I'm not allowed to divide by is 0. So if our denominator, x squared minus 7x plus 12, is 0, the function becomes undefined because we can't divide by 0. So we want our denominator here to not be equal to 0. Even though I'm using a not equal to symbol instead of equals, the way we're going to solve this is exactly the same as if I did put equals. I can either factor or use quadratic formula. Here, we'll factor, and x squared minus 7x plus 12 factors to x minus 3 times x minus 4. Now, we would set each factor not equal to 0, because in order for a product to not be 0, then both factors cannot be 0, which means x cannot be 3, and it cannot be positive 4. So our domain is every number except for 3 and 4. Now, how would I write this in interval notation? My value for x could be anything smaller than 3. So we would have -infinity to 3, union. Well, it could also be anything between 3 and 4. So we'll have the interval 3 to 4. And finally, our value of x could be anything bigger than 4. So we would have union union 4 to infinity. So I just took the real number line, removed 3 and 4, creating 3 intervals. So my domain of our function for g of x is negative infinity to 3, union 3 to 4, union 4 to infinity. So now we'll find the domain of h of x, which equals negative 3 minus the square root of 2x minus 3. In this function, we don't see division, so we don't have to worry about dividing by 0, but we do see an even root. Square root, remember, has index 2, which is an even number. So what is our restriction to the square root operation? Well, we can't take the square root of a negative number and get a real number, and we are only concerned with our function equaling real numbers. So the expression inside of our square root cannot be negative, meaning it's either positive, meaning 2x minus 3 would be greater than 0, or it could be 0 itself. So 2x minus 3 must be greater than or equal to 0. Because again, if 2x minus 3 is negative, I try to take the square root of a negative number, I get something imaginary, which is not allowed here. Now I have an inequality to solve, and when we solve our inequality, we get x is greater than or equal to 3 halves. This inequality tells me the smallest value of x I can plug into my function and still get a real number is 3 halves. So my interval will start off with a closed bracket and 3 halves, but I can plug in any number larger than 3 halves and my function will be defined. So I'll end with infinity. My domain for h of x is the interval 3 halves to infinity with a closed bracket around 3 halves. Now we're going to find the domain of k of x, which equals the square root of x plus 3 all over x minus 1. Now here, if we look carefully, we do see division. Well, the one number I'm not allowed to divide by is 0. So x minus 1 cannot be 0. But I also see an even root. And remember, I can't take the even root of negative numbers, otherwise they'll be imaginary. Well, the expression underneath the even root is x plus 3. So in order for my function to be real, x plus 3 has to be non-negative. In other words, x plus 3 must be greater than or equal to 0. So I have these two inequalities that have to be true simultaneously. X minus 1 cannot be 0, and x plus 3 must be greater than or equal to 0. If I solve both inequalities, the first tells me x cannot be 1. The second tells me x is greater than or equal to negative 3. To help understand how to set up our interval notation, we're going to draw a little number line. The two numbers I'm concerned with on my number line are negative 3 and positive 1. The reason why I'm putting a closed dot on negative 3 is because the inequality x is greater than or equal to negative 3. And because of the fact that I'm saying x cannot be 1, I am putting an open dot. Thanks to the x being greater than or equal to 3, I know I would have to shade to the right of negative 3. But because the x cannot be 1, I can't shade over 1. So you can see that the graph representing the possible x values I can plug into my function would be all the values from negative 3 to 1, but negative 3 would be included, 1 would not, union, well then anything bigger than 1, which would be 1 to infinity. And there is the domain of our function k of x. It would be negative 3 to negative 1 with a closed bracket on negative 3, union 1 to infinity, with parentheses around 1. Oftentimes, one equation is not enough to be used to describe a function, in which case we start using what we call piecewise functions. A piecewise function is a function where multiple equations are used to represent the function. Below, an example of a piecewise function is f of x equals 1 if x is less than 1, f of x equals the square root of x minus 1 plus 1 if 1 is less than or equal to x less than 5, or f of x equals 2x minus 6 if x is greater than or equal to 5. The way we use piecewise functions is first we check what condition the value we're trying to plug in for x is satisfied. For example, if I want to evaluate f of negative 2, that means I'm trying to plug negative 2 in for x. Well, taking a look at the conditions, negative 2 is less than 1, which means I'm using that first equation to evaluate f of negative 2. Well, according to the first equation, f of negative 2 is just equal to 1. To evaluate f of 2, that means we're plugging 2 in for x. But which condition does x equal 2 satisfy? Well, 2 is not less than 1, so we won't use the first equation. But 2 is in between 1 and 5, which means we're going to use the second equation. And we don't have to check the third equation because piecewise functions are functions. That means for every x, we should get one function value out of it, so the conditions will not overlap. So using our second equation, replacing x with 2, we have that f of 2 equals the square root of 2 minus 1 plus 1, which equals 2. Next, we'll evaluate f of 10, which means we're plugging 10 in for x. Well, 10 is not less than 1, 10 is not between 1 and 5, but 10 is greater than or equal to 5. So to evaluate f of 10, we need to use the third equation, and in the third equation, we'll plug 10 in for x, and we get that f of 10 equals 14. Lastly, we're going to evaluate f of 5, which means we're replacing x with 5. 5 is not less than 1, so we won't use the first equation. 5 is greater than or equal to 1, but is 5 less than 5? No, 5 is equal to 5, so 5 does not satisfy the second condition. Is 5 greater than or equal to 5? Yes, it is, because 5 is equal to 5. So to evaluate f of 5, we're going to use the third equation. Replace x with 5, we get that f of 5 equals 4. Now we're going to graph our piecewise function. When we graph a piecewise function, we're going to graph it a little bit at a time, working on one equation at a time and making sure we pay attention to the condition. First, we're going to graph the equation y equals 1, which recall is going to be a horizontal line. So if we were to just graph y equals 1 without any conditions, you'd have a horizontal line that we see here. However, keep in mind, we can only use this equation when x is less than 1. So any part of the graph of y equals 1 that is to the right of 1, I need to erase. And I'm only going to keep the part of the graph to the left of 1. Now, at x equals 1, I can't actually use y equals 1 to evaluate the function. So I'm going to put an open circle to signify that the equation y equals 1 stops at this point where x equals 1, but this point is not actually part of the graph of f of x. Now, the next equation is the square root of x minus 1 plus 1. We're going to skip that for now, and we're going to go to the 2x minus 6, since y equals 2x minus 6 is also a line, which would be really easy for us to graph. The slope of our line is 2, our y-intercept is -6. So using the y-intercept, we would have that our y-intercept is down there at the point 0, -6. And then using the slope, which is the same as 2 over 1, we will rise 2 and go right 1. And that'll give us this extra point here. And now we can draw our line. Now recall that the condition for when f of x equals 2x minus 6 is when x is greater than or equal to 5. So going to my graph, when I plug 5 into 2x minus 6, I do get 4. So I have this point located here at 5, 4. And I want to make it a solid dot because I can plug 5 into 2x minus 6 to evaluate my function. Now, because I can only plug in values that are 5 or larger in the 2x minus 6, I want to erase the parts of the graph where x is smaller than 5. And there is the graph of 2x minus 6 for when x is greater than or equal to 5. Now we're going to turn our attention to the square root of x minus 1 plus 1. In order to graph this equation, we're going to plug values in since we haven't quite studied how to graph it using its properties. Now, using the table, I do want to start off with the ends of my condition, which here would be 1 and 5. Even though I can't plug in 5 into the square root of x minus 1 plus 1 to evaluate my function, it will at least tell me where the curve stops to help me make my graph. Then we're going to pick a few other values. I'm going to pick 3, which is right in between 1 and 5. And we're going to plug these values of x into our square root of x minus 1 plus 1. If I plug in 1, we get 1. If we plug in 3, we get square root of 2 plus 1, which is approximately 2.414. And if I plug in 5, we get 3. So at 1, 1, I'm going to put a closed dot, which is going to override the open dot we had before when we graphed the y equals 1. Whenever a open dot is overlapped by a closed dot, we still keep the closed dot. Then the 3, 2.414, which is approximately there. And then the 5, 3, which is going to be an open circle since we can't actually plug in 5 to the square root of x minus 1 plus 1 to evaluate f of x. And then we connect the dots. And we have this little gradual curve here for the square root of x minus 1 plus 1. There's the graph of my function. One thing to keep in mind, we did graph a function. After you graph, check to make sure your graph passes the vertical line test. That way, you're not accidentally putting 2 closed dots where 2 closed dots don't belong. One use for absolute values is to redefine the absolute value operation. The absolute value of x, which we learned before represented the distance between 0 and x, can be defined as either equaling x if x is greater than or equal to 0. This is because whenever I plug in a positive number or a 0, the absolute value of that positive number or 0 will be itself. So here, absolute value of x would be x. However, if I take the absolute value of a negative number, meaning x is less than 0, that negative number becomes a positive number. It becomes its opposite. Well, the way we can obtain the opposite of a number is by multiplying that number by -1. So the absolute value of x equals negative x if x is less than 0. And since x is already negative, negative x will become positive. So it still lines up with the definition of absolute value. This definition makes it much easier to graph f of x equals absolute value of x. This is because we can graph the 2 parts that make up the piecewise definition of the absolute value of x and graph each one at a time. This problem of how to graph f of x equals absolute value of x will be left for you as a homework to try out.